Susan is an astronomer working the night shift at this observatory. Her job is to study stars in different parts of their life cycle. Susan studies the amount of radiation stars give off, their size, their color, and how they progress from birth to death. Click the highlighted parts of the image to learn more about Susan's work. When done, click the Next button to investigate the life cycle of stars. There are thousands of stars in the night sky. Susan uses the telescope to scan the sky, making observations of distant stars and galaxies. Susan has a particular interest in discovering stars that are very young. Stars are born and eventually they die. Susan observes and makes calculations of stars in various stages of their life cycle, such as the nebula, red giant, and supernova stage. Susan has observed that large stars have a different life cycle than small stars. Life stages are dependent on the size of the star. Susan's observatory is located high on a mountain, which allows her to make her observations above the cloud cover. The observatory building, shown in this time-captured video, rotates so that she can get a clear, complete view of the sky. Welcome to the lesson, The Life Cycle of Stars. In this lesson, you'll learn how to describe the stages in the life cycles of stars. The vocabulary words for this lesson are nebula, white dwarf, supernova, neutron star, HR diagram, and main sequence. Click each word to find out more about it. Just like humans, stars are born, grow old, and die. But stars live and grow over millions or billions of years. Humans can see each star only at certain stages of a star's life cycle. Stars are born in regions called nebulae. Click play to learn about some of these areas. This image from the Hubble Space Telescope shows the N11 nebula in a nearby galaxy. The process of star formation gives N11 its interesting appearance. When stars form and during the early stages of their life cycle, dust and clouds are blown away from the stars. 3 generations of stars have formed within N11, forming layers of gas and dust within the nebula. As you have seen, stars form in nebulae. Click the dots on the line to learn how this happens. A nebula is a large cold cloud of gas and dust in interstellar space. Gravity causes gas and dust in some regions of a nebula to collapse rapidly. The gas and dust then form a hot, dense core called a protostar. The protostar in this image is inside a dark cloud. As more and more gas and dust condense, the core of a protostar becomes hotter and hotter. At extremely high temperatures within a protostar, atoms lose their electrons, leaving only nuclei. In this image, the nuclei of 2 different forms of hydrogen combine or fuse to form helium. This helium has 2 protons and a neutron. Once nuclear fusion begins, stars emit visible light and other forms of energy. Larger, brighter stars release more energy than smaller, dimmer stars do. Once a star is formed, it continues to change throughout its life cycle. Click play to learn more about the different stages in a star's life cycle. For most of a star's life cycle, fusion takes place in the core of the star. Stars fuse hydrogen nuclei, forming helium nuclei. The fusion of hydrogen nuclei to form helium nuclei releases energy as light and heat. This stage of a star's life cycle will last for millions of years. During this stage, the star is called a main sequence star. Eventually, the process of nuclear fusion slows. At this point, a star has reached the final stage of its life cycle. When the fusion process stops, stars eject matter into space and lose mass rapidly. Then only the core of a star remains. In this final stage, the core will take one of various forms, depending on the original mass of the star. You've learned a lot about how stars form. Which image shows an area where stars are forming? Click on your answer. Good job! Stars are formed in regions of space called nebulae. Stars form within nebulae. In some areas of a nebula, gravity causes the gas and dust to collapse quickly. As the gas and dust condense, they form a hot, dense protostar. As the temperature in the protostar rises, fusion begins, releasing huge amounts of energy. A star spends most of its life cycle as a main sequence star. Eventually, however, there is no hydrogen left in a star's core. The star ages and eventually burns out. Click the images to learn more about the stages in the life of a low-mass star. The star becomes a giant and begins to fuse helium nuclei into carbon nuclei. When fusion in the star stops, the outer layers of the giant star are ejected into space. The expanding shell of gases is called a planetary nebula. This is different from a nebula where stars are born. The planetary nebula disappears once the star cools. The exposed core of the star is called a white dwarf. A white dwarf is the leftover core of a low-mass or medium-mass star. A star may stay in this stage for billions of years. During that time, the star is changing little by little. Click play to find out more about white dwarfs. The core of a low-mass or medium-mass star that has lost its outer layers is a white dwarf. Over billions of years, the energy stored in the white dwarf is radiated into space. The white dwarf cools and decreases in luminosity. You've learned about the life cycle of a low-mass star. Can you label each stage in a star's life? Remember that you can roll over the images to learn a bit about them. Good work! A protostar develops as the dust and gas collapse in a nebula. Fusion begins and a main sequence star is born. When fusion slows, a red giant develops. When fusion stops completely, the red giant becomes a white dwarf. You've learned a lot about what happens when fusion ends in a low-mass or medium-mass star. But some stars are much more massive than the Sun. The life cycle of these high-mass stars is a bit different. Click each image to find out more about the life cycle of a high-mass star. When helium fusion in a high-mass star ends, other types of fusion begin that involve the fusion of nuclei into elements that are heavier than carbon. The star expands to become a blue giant. The star does not remain a blue giant for long. The star then expands to become a supergiant with high luminosity. A supergiant does not become a white dwarf like a red giant does. Instead, when fusion ends in a supergiant, there is a huge explosion called a supernova. Click each image to learn more about a supernova. When the fusion of heavy elements in a supergiant ends, the core of the high-mass star collapses. This triggers a supernova, which is when a high-mass star collapses and throws its outer layers into space in a violent explosion. A high-mass star may end its life cycle as either a neutron star or a black hole, depending on how massive the star was to begin with. Neutron stars are stars that have collapsed under gravity, to the point where the electrons and protons in the star have smashed together to form neutrons. A neutron star forms during a supernova when the core of a supergiant star contracts. The core of the supergiant becomes a very dense sphere of closely packed neutrons. The core of a supergiant star with an extremely high mass may collapse to form a black hole. A black hole is an object that cannot be seen because its gravitational attraction is so strong that no radiation, including light, can escape. Although we cannot observe a black hole itself, we can observe its gravitational influence on surrounding stars and gas. Which choices correctly describe what may happen after a high-mass star experiences a supernova? Click all correct answers. Good job! The most massive supergiants become black holes. That's right! Supergiants may become neutron stars. When the fusion of heavy elements ends in a supergiant, the core of the high-mass star collapses, triggering a supernova. High-mass stars may end their life cycle as either neutron stars or black holes, depending on how massive they are when they start out. Recall that luminosity and absolute magnitude describe the actual brightness of a star. In general, hotter stars are also brighter stars. Here, you see a Hertzsprung-Russell diagram, which illustrates the relationship between a star's surface temperature and its absolute magnitude. This diagram is also referred to as an HR diagram. Click the parts of the chart to learn more about HR diagrams. Hot stars are located on the left side of the diagram. The hottest stars are blue giants. Blue giants produce an enormous amount of energy. They are very hot and their diameter is very large. White dwarfs are very dim but very hot and are plotted at the bottom of the HR diagram toward the left. The x-axis shows the surface temperature of a star. Notice that the higher temperatures fall on the left side of the axis. The main sequence is the region where most stars lie on the HR diagram. Stars spend most of their lives as main sequence stars. The main sequence has a diagonal pattern that runs from the upper left of the diagram, where stars that are bright and have high temperatures are plotted, to the lower right of the diagram, where stars that are dim and have low temperatures are plotted. Red giants and supergiants are the brightest stars. They are plotted at the top right of the HR diagram. Cooler stars are located on the right side of the diagram. The coolest stars are red dwarfs. Red dwarfs are small main sequence stars. Their surface temperature is below 4,000 kelvins. The y-axis shows the absolute magnitude of a star. Stars with an absolute magnitude of less than +5 are brighter than the sun. The sun is a medium-mass star. Its life cycle will follow the same pattern as other medium-mass stars. Note that the sun does not actually move this way through space. As stars enter new phases in their life cycles, they are replotted on the HR diagram, based on their changing magnitude and surface temperature. Click the dots on the line to learn about the sun's life cycle. The Sun is a main sequence star with an absolute magnitude of +5 and a temperature of about 6,000 kelvins. When nuclear fusion slows in the Sun, it will become a red giant like this star. At that point, the Sun would be plotted in the upper right area of the HR diagram. At that time, the Sun will be brighter, but it will have a cooler surface temperature. When the outer layers of the giant star are ejected into space, the Sun will become a white dwarf and will be plotted in the lower left quadrant of the HR diagram, indicating that it is now dimmer but hotter than before. You've just learned about the HR diagram. These images show 4 types of stars that are found on the HR diagram. See if you can identify each kind of star. Drag each label to the correct image. You got it! The HR diagram illustrates the relationship between the temperature of stars and their brightness. Low-mass stars and high-mass stars have different life cycles. Drag each image into the correct category box. That's right! High-mass stars experience a supernova. Depending on the mass of the original star, the star may then become either a neutron star or a black hole. Low-mass stars become red giants and then, after their outer layers expand and are ejected, white dwarfs. Describe the role of nuclear fusion in the life cycle of a star and what happens when nuclear fusion in a star's core stops. Type your answer in the box. When you are satisfied with your answer, click OK. You've learned a lot about the life cycle of stars. Let's review the main ideas from the lesson. Stars form in nebulae. A nebula is a large cloud of dust and gas in interstellar space. Stars form from this interstellar dust and gas. The fusion of 2 or more nuclei releases energy, including light and heat. Nuclear fusion plays a role in the luminosity, temperature, and classification of a star. The life cycle of a low-mass or medium-mass star progresses from the main sequence to red giant and finally to white dwarf. These stars become red giants when fusion in their core slows down. When fusion stops, the outer layers of the star are ejected, and the remaining core becomes a white dwarf. High-mass stars eject their outer layers in a supernova explosion. The core of a high-mass star will then become a neutron star or black hole, depending on the original size of the supergiant. Where a star is plotted on an HR diagram indicates the star's temperature and absolute magnitude or brightness. The HR diagram also can be used to illustrate the life stages of stars, as stars change position on the HR diagram as they age. Now that you've finished this lesson, if you wish, you can go back and review any part of the lesson again.